Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our lecture. This is the thermal management part 3. So in part 1 and part 2, we already discussed the theoretical part for the thermal management. So in this third part and final part for this chapter, we will discuss some examples regarding the thermal management. Okay, this is the first example. In this example, we are looking at the isolated forward converter circuit, and we are given several thermal parameter for Schottky diode and also for the Mosfet. So in this circuit, we have two diode here, okay, and then we have one Mosfet here. Okay, this the temperature junction maximum. So this is the maximum junction temperature for the Schottky diode is 175 degrees C, and then for the Mosfet is 150 degrees C. And for the thermal resistance, this is from junction to sink. Okay, this is given as 2 degrees C per watt, and then for the Mosfet is 0.42 degrees C per watt. Okay, in this question, it required us to determine a single heatsink thermal management design for the Mosfet and Schottky rectifiers operating at 50 degrees C ambient temperature and with the minimum 20 degrees C Schottky junction temperature boundary margin. Okay, so what it means by having a single heatsink thermal management? Okay, the single heatsink means that we have three components that are switching. Okay, this is the Mosfet, and this is the diode that the current will turn off and turn on based on the switching of the Mosfet. So if the question asks you a single heatsink thermal management, it means that we want to design or to select a heatsink that on the heatsink we will put all the three components, two diode and one Mosfet on one heatsink. So that's the term single heatsink thermal management design. So we will look how we can design the heatsink that will satisfy all these conditions. We have the 50 degrees C ambient temperature, and we have to design it with minimum 20 degrees C Schottky junction temperature boundary margin. Okay, for the thermal management design question, usually you will be given this power dissipation versus the temperature graph, and then this graph will contain all the trend or the characteristic curve for the Mosfet, the Schottky 1 and Schottky 2. Okay, so in this case we have to find the Schottky 1 boundary temperature. Okay, so we have to select this one. We have to determine the boundary temperature of this component first, because we can see that this component will have the uptrend curve, okay, earlier at this point compared to these two curve. Okay, so we have to select the Schottky one as a starting point. So to find the boundary temperature, we have to, okay, first we have to mark here the ambient temperature, which is given at 50 degrees C, and then we have to draw a straight line to this curve. Okay, and this line will touch only one point of this curve. So let's say from here, from my eye, I can see that the boundary point here is at 160 degrees C. Okay, so maybe if you Yeah, I mean different people, different interpretation. Maybe you draw this but you think this is 165, so no problem. If you draw this and then you say that this is the boundary, because you see that, oh, this is the point that it touch one point of this curve, right? So you mention that you will select 165 as your boundary temperature. Okay, for myself I select 160 degrees C. Okay, so this is the boundary temperature for Schottky 1, which is 160 degrees C. Okay, so in the question it mentioned that we have to select a minimum 20 degrees C boundary margin. Okay, so 160 minus 20 is 140. Okay, so the junction temperature of Schottky 1, okay, we should select it to be 140 degrees C maximum. Okay, so this is the 20 degrees C from 160 to 140. Okay, so this is the maximum temperature that you can set for junction temperature for Schottky 1. Okay, so let's say if you want to select 130, it's also fine, because you have fulfilled the 20 degrees C boundary margin. So the margin from the boundary to this one, so if you want to select lower than that, it should be fine as well. Okay, so in this case I want to really select at that particular point 140, so I select that as a my uh, junction temperature for Schottky 1. So when I select this one as my junction temperature, so when you draw a straight line to this y-axis, you'll find uh, the power dissipation, okay, at this temperature is 4 watt, right? Okay, and then we have to find the T-sink, which is the temperature at the heatsink. Okay, because we know that the temperature at heatsink should be the same for all the component. Okay, so now we want to find the temperature at the heatsink based on the value that we get from the Schottky 1. Okay, so we have to use this equation. The T-sink equals to T junction Schottky minus the power, okay, power operation at Schottky 1 multiplied by RTH junction to sink. Okay, because we have the junction temperature, we already set the junction temperature, and then we want to find the heat sink. The S is heat sink. Okay, and then we have this value of RTH. Okay, for this case we have 140 minus the power here is 4 multiplied by 2, the value given in the question. So the value that we get for T-sink is 132 degrees C. Okay, so this is the junction temperature, and based on the thermal resistance that we have, we will get the T-sink equals to 132 degrees C. Okay, and then based on this, we know that for the temperature, the heatsink temperature will be the same for all the three components. Okay, why it is the same? Because all the three components will be put on the same heatsink. So the temperature that will be common is this one, the T-sink. Okay, so now we can draw. Okay, because this is the Schottky 1 and then this is Schottky 2. We know that, okay, this straight line is the thermal resistance, okay, the slope for thermal resistance, that I mean 2 degrees C per watt that we draw just now. Okay, so we know that the Schottky 2 and Schottky 1 both have the same thermal resistance. So when I draw this one to this one, and then I further up increase to this slope will be the same. This is 2 degrees C per watt slope. Okay, so when I draw this one until the Schottky 2 curve here, at this point this is the what we call the junction temperature for Schottky 2. Okay, so in this case we have junction temperature Schottky 2 equals to 150 degrees C. Okay, so because why we can use this straight line, because the Schottky 1 and Schottky 2 have the same thermal resistance and the same slope. Okay, so you can just draw this one and then you get this temperature. Okay, and then when we draw a straight line to this power dissipation axis, we will get the power of Schottky 2 is 8.9 watt. Okay, the dissipated power. Okay, now the remaining one that we have to do is we have to find the temperature, the junction temperature for Mosfet. Okay, and then the information that we have is we have the RTH junction to sink for the Mosfet is 0.42 degrees C per watt. Okay, this is the value 0.42 degrees C per watt. So based on this, okay, we know that for this value 0.42 degrees C per watt, so it's equal to this. Okay, but if you want to draw a 0.42 degrees C increment, okay, in the graph that we have, so it is difficult because it's very small, 0.42, which is very small. So what if we try to find how much the power change if we increase the temperature by 3 degrees C? Okay, 3 degrees C is possible to draw because it's not that small, right? Okay, compared to this 0.42 is very small. So we want to find how much power change if the temperature is increased by 3 degrees C. So we have to use this one, 0.42 degrees C per 1 watt equals to 3 degrees C per x watt. So this x we have to find it, how much the power dissipate, power change, okay, when we increase the temperature by 3 degrees C. So when you find the value of x, the value is 7.14 watt. Okay, so that one we have to draw. Okay, we have to draw here. Okay, we have, this is the temperature of the heatsink, and then okay, we know that at this point, okay, this is 132 degrees C. So if we want to have the increment of 3 degrees C, so it is 132 plus 3, which is 135, which is in the middle here, in the middle of okay, this box from 130 to 140. The middle here is 135, and then the power that related to that increase is 7.1. so 7.1 is at this point. Okay, this is 7. Okay, just increase a little bit, 7.1. so you have to draw a straight line from here to this point. Okay, so this is the slope of 0.42 degrees C per watt. Okay, so what we will use after that is we draw a straight line from this point to here, and then we will cross one point at this Mosfet curve. Okay, this line that going down here will cross one point at this Mosfet curve, and the value here is at this point we can draw it to the y-axis, and we will find that power operation during that time is 4.5 watt. So now that we already got all the power dissipation for Schottky 1, Schottky 2 and the Mosfet, we can find the total power. The total power is, okay, you will just add all of them, 4 plus 8.9 plus 4.5, the total power of 17.4 watt. Okay, and then this one, finally you want to find the RTH sink to ambient. Okay, this is the value of the thermal resistance of the heatsink that we should design. Okay, so we have to consider all the temperature, the heatsink temperature minus the ambient temperature, divide by total power dissipated from all the device that we put on the heatsink. So we already calculate this. The power total is 17.4. The heatsink temperature is 132, and then we have the ambient temperature of 50 degree. So when we solve this equation, we have the RTH sink to ambient is equals to 4.71 degrees C per watt. So this is the thermal resistance for the heatsink. So if you want to find uh, the heatsink for this operation, or to cool these three devices, we have to use this value for the thermal heatsink. So if you want to see graphically, I mean in terms of the drawing, we have the total power of 17.4 watt. Okay, this is the line, and then we can connect this to this ambient temperature. So this is the thermal resistance slope for the heatsink. Okay, it is required to cool down all the component that we have, which is 2 Schottky diode and 1 Mosfet. Okay, now we move to the second example. So in this circuit, we still use the forward converter. Okay, and then we have the RTH junction to case, which is given 1.5 degrees C per watt, and then RTH case to sink 0.5 degrees C per watt. Okay, if you compare this to the first example, in the first example it gives the value of RTH junction to sink. Okay, so in this case it gives the junction to case and then case to sink. Okay, so based on this value, you can already determine that the value of RTH junction to sink is equal to 1.5 plus 0.5. Okay, so because you have the junction to case and then case to sink, so this value can be added together to find the junction to sink. Okay, well, we have junction to case, case to sink. If you want to find the RTH junction to sink, just add this value together. Okay, in this question it asks us to determine the common heatsink design requirement for thermal management of the Schottky rectifiers. Okay, this is the key here. Okay, remember that this single heatsink requirement is only for Schottky rectifiers. Okay, so only for these two. So if you add another one for the Mosfet, it will be wrong, because the question asks you only for the Schottky diode. Okay, so you have to be really careful. Okay, sometimes for the thermal management circuit, it doesn't have to be forward converter circuit. Okay, I can in the question we can give you flyback converter, we can give you push pull converter. Okay, so you have to know how many components involved when you want to design the heatsink. Okay, sometimes there will be maybe 2 diode and then 2 MOSFET, so you have to base your calculation based on that 4 component, let's say for 2 diode and 2 MOSFET. Okay, so you have to if any given circuit that you will be given in the question, so you have to know how many, you have to be really careful on how many components that you should design the heatsink for. Okay, so in this example, we have the ambient temperature of 50 degrees C. Okay, and then in this question, it already give you the junction temperature. Okay, in the previous one, example 1, you have to determine your own junction temperature. You have to set which junction temperature you want your Schottky 1 to operate. But in this question, it already give the junction temperature of Schottky 1, which is at 125 degrees C. Okay, so that will be different. And then this is okay, so this is another type of question that we can give. Okay, now that we know that this temperature is already given, the Schottky one, which is 125 degrees C, so straight away we can draw a straight line here. Okay, and then we draw a straight line to the y-axis, and we will get the dissipated power at this temperature is 4 watt. Okay, now that we know the junction temperature for the Schottky diode, we can determine the heatsink temperature. Okay, we know that the heatsink temperature will be the T junction Schottky 1. Okay, the junction temperature that we already marked before this, minus the dissipated power multiplied by the thermal resistance. Okay, but you have to be really careful. This is the thermal resistance from junction to sink, because we want to find the heatsink temperature. Let's say if you want to find the case temperature, T case, okay, you just use this value 1.5. But in this case, because we want to find the sink value, so from this value, the junction, we have to use the RTH junction to sink. Okay, why junction to sink? Because we want to find the heatsink temperature. Okay, so RTH junction to sink, like I mentioned before, you have to add this value RTH junction to case plus RTH case to sink. You add this value together. Okay, so when you replace the value here, this is 125 minus the power that we draw from the graph is 4, multiplied by 1.5 plus 0.5, which is 2 inside here. Okay, and then when we solve this, we will get 117 degrees C. So this is the heatsink temperature. Okay, we want to because the heatsink will be a common temperature, so T-sink Schottky 1 and T-sink Schottky 2 will be 117 degrees C as well. Okay, so like before, we draw a T-sink, we mark at this 117, and we can draw a straight line from here to this point. Okay, because the thermal resistance is the same for Schottky 1 and Schottky 2, because they are the same component. Okay, and then from this, we can draw a straight line to the x-axis here, and this is the junction temperature for Schottky 2, which is 135 degrees C. Okay, and then when we draw a straight line to the y-axis, we know that the power dissipated at this point is 9 watt. Okay, so if you want to just verify it, this is other way to verify for junction, the T-sink for Schottky 2. So we have the temperature here, the one that we determined by drawing a line just now, okay, which is 135 minus the power dissipated here multiplied by 1.5 plus 0.5, which is 18. Okay, so 135 minus 18 is 117. So this is the same temperature that that we should get for Schottky 1 and Schottky 2, because this is the heatsink temperature, which is should be the same for the component that we want to put on the heatsink. So next one is we have to find the total power. Okay, we have the power for Schottky 1 4, and for Schottky 2 we have 9, and the total power is 13 watt. Okay, and then when we want to find the RTH sink to ambient, okay, we have to have the T sink, the temperature at the heat sink minus the ambient temperature divided by the total power, and then we will get the RTH sink to ambient equals to 5.15 degrees C per watt. Okay, so this is the thermal resistance for the heatsink. So if you want to see the graph or the line, so this is the slope of the thermal resistance that we just calculated just now. Okay, this is example number 3. So in this example we are still using the forward converter. Okay, and then we are given several thermal characteristic. The first is the junction temperature, the maximum junction temperature for Schottky, and then for Mosfet, and then we are given the RTH junction to case for both Schottky and Mosfet, and then we are given the RTH case to sink for both of them as well. Okay, so in this question is a little bit different, because instead of we have to design ourselves the junction temperature and then finding the heatsink temperature, in this question it already given the heatsink temperature, which is at 130 degrees C. Okay, and then we have to find for the given thermal resistance value, okay, based on this value, the thermal resistance value, determine the following. We have to find the Schottky 1, Schottky 2 and Mosfet operating junction temperature. Okay, we already know that when we have a common heatsink, single heatsink, so all of them will have the same heatsink temperature, which is at 130 degrees C. So now we have to find the Schottky 1, Schottky 2 and Mosfet operating junction temperature. And then we have to find the case temperature. And finally, the thermal resistance of the heatsink if the ambient temperature is 40 degrees C. Okay, so we will look at the step to solve all these 3 questions. Okay, the heatsink temperature is already given, which is at 130 degrees C. Okay, and then we want to find the junction temperature for Schottky based on the value of RTH junction to sink. Okay, for Schottky, okay, this is the RTH junction to case and this is case to sink. So if you want to find the RTH junction to sink, we have to add both of them together. So 2 plus 0.5, we will get 2.5. So we have 2.5 degrees C per watt, which is a little bit small to draw. So what if we try to find how much the power change if the temperature is increased by 10 degrees C, which will be much easier to draw. So instead of this, we want to find the value of X here. 2.5 degrees C per watt equals to 10 degrees C per x watt. So the value of x is 4 watt. Okay, now we already mark here the heatsink temperature, which is 130 degrees C. So remember that we want to draw a line, okay, at this point. We have to, okay, this line, if you see closely, the increment of 10 degrees C, okay, from 130 to 140, and then the power is increased by 4. Remember our calculation for the power, when we increase the temperature by 10 degrees C, the increment of power is 4. So this is the straight line that we want to draw. Okay, and then we get, okay, suddenly we can get this value straight away. Okay, the junction temperature of Schottky 1 is 140 degrees C, and then the power dissipated for Schottky 1 is 4 watt. Okay, and then, okay, because they are both using the same, or both are having the same thermal resistance, so we can use this straight line. And then at this point, the value of junction temperature of Schottky 2 is 152 degrees C. Okay, if you draw a straight line here, you will get 152, and then the power dissipation is 8.9 watt for this one. Okay, now we already got the junction temperature for Schottky 1 and junction temperature for Schottky 2, which is 140 and 152 respectively. Okay, next we want to find the junction temperature for the Mosfet. Okay, and then this is based on this value, 1.4 plus 0.6 degrees C per watt. Okay, you have to add both of this value. Okay, we have to draw 2 degrees C per 1 watt, which is, yeah, I mean, a little bit difficult to draw. So we want to find how much power, okay, when we increase the temperature by 10 degrees C. So we get in this question, we get x equals to 5 watt. So now, okay, we have to draw, we increase the temperature by 10, and the power will increase by 5. So remember, this is the point, so we have to draw a straight line from here to this point, okay, at this particular point. Okay, and then we can draw okay, the line when it cross the Mosfet curve here, so you will get the temperature at this point, okay, at this particular point. So the junction temperature for the Mosfet is 138 degrees C. And then when we draw a straight line to the y-axis, you will get the power of the Mosfet is 4.6 watt. Okay, so this is the operating junction temperature for Schottky 1, Schottky 2, and the Mosfet. Okay, you have junction temperature Schottky 1, Schottky 2, and junction temperature for the Mosfet 138. Okay, now we want to find the solution for the next question, which is the case temperature of the Schottky 1, Schottky 2, and Mosfet. We already have the junction temperature for all the three components, so we can use the equation. Okay, the temperature case of the case temperature for Schottky 1 is equal to the junction temperature of Schottky 1 minus the power dissipation of Schottky 1 multiplied by RTH junction to case. So because we want to find the case temperature, so we have to find the RTH junction to case. Okay, we have to use the junction to case thermal resistance. So in this case we have 2. Okay, 140 minus 4 multiplied by 2 will have 132 degrees C. So this is the case temperature for Schottky 1. For Schottky 2, the same procedure. You have to use the temperature for junction temperature for Schottky 2 minus the power dissipated multiplied by RTH junction to case. Okay, then we will have the case temperature for Schottky 2 is 134.2 degrees C. And finally, for the Mosfet, the same procedure. We have the temperature of the junction temperature of the Mosfet minus the power that we already attained here, 4.6 multiplied by RTA junction to case for the Mosfet, which is 1.4. So in this case we get the T case Mosfet is 131.56 degrees C. And finally we want to determine the thermal resistance. So this should be easy because you already find all the power dissipation for all the 3 components. You just add them together. Okay, the total power is 17.5. Okay, and finally you can find the RTH sink to ambient, the thermal resistance for the heat sink. T sink minus the ambient temperature, which is 40, divided by P total, which is 17.5, and then you will get 5.14 degrees C per watt. Okay, so if you want to see from the graphical point of view, so this is the value of the thermal resistance slope. Okay, this is the example number 4 for the thermal resistance chapter. Okay, still we use the forward converter circuit. Okay, and then we have the junction temperature maximum for Schottky and Mosfet. Okay, this is the common one. And then we have the thermal resistance from junction to sink, which is 3.33 and then 4.44. Okay, so in this question it asks us to determine the common heatsink design requirement for thermal management of Schottky rectifiers and Mosfet. So this question asks us for Schottky rectifiers and Mosfet. So we have to include all the 3 components, Schottky 1, Schottky 2 and the Mosfet. And then the ambient temperature is set at 35 degrees C. Okay, and then if the operating junction temperature of Schottky 2 is 140 degrees C. So in this question, it already gives the Schottky 2 junction temperature. Okay, remember this is the Schottky 2 junction temperature, not the Schottky 1. Okay, so this is the Schottky 2 curve. Okay, and then it already given the junction temperature of Schottky 2 at 140 degrees C. So you can just draw a straight line here. Okay, and mark this one. So this is the power dissipation. Okay, when the Schottky 2 is operating at 140 degrees C, the power dissipation is 9 watt. Okay, now the next step, if we want, we have to find the heatsink temperature. So now we already have the junction temperature. We already from the curve there, we get the value of power dissipated, which is at 9 watt, and then we have RTH junction to sink. So 140 minus 9 multiplied by 3.33, we will get 110.03 degrees C. Okay, which is we can round it to 110 10 degrees C. So we have here the T-sink is 110. So we can draw a straight line from here. This is the value of the thermal resistance from junction to sink. Okay, and then we know that the thermal resistance for Schottky 1 and Schottky 2 is the same, so you can share this same what we call the thermal resistance slope, and then we can the one that cross the Schottky 1 slope here. Okay, this will be the operating junction temperature for the Schottky 1, which is 122 degrees C. So this is the junction temperature of Schottky 1. Okay, and then you can already determine the operating dissipated power. Okay, so from here you see the value is 4 watt. Okay, and finally we have to determine the junction temperature for the Mosfet. The information that we have is the thermal resistance of junction to sink for the Mosfet is 4.44 degrees C per watt. And okay, we have the common value of the heatsink. So after that we want to determine the junction temperature for the Mosfet. Okay, now we have to draw some line. Okay, you know that the value of 4.44 degrees C, the power will increase by 1. So when we want to find the value of, okay, we want to draw a 10 degrees C line, so we have to find the value of x. Okay, and then we will get x equal to 2.25 watt. This is the value, 2.25 watt. So the increase of 10 degrees C will increase the power by 2.25 watt. Okay, so this is the junction, the heatsink temperature. Okay, when we increase by 10 degrees C, and then here 2.25 at this point. Okay, so we have to draw a line here. Okay, remember you have 10 degree and then 2.25. You draw a line to drag through that point, and then the line will cross some point at the Mosfet curve. So at this point, this is the junction temperature for the Mosfet, okay, which is 130 degrees C. Okay, and then when you draw a straight line to the y-axis, you will get the power dissipated, okay, at that operating point is 4.4 watt. Okay, and then we have to find the total power. Okay, we have the Schottky 1 plus Schottky 2 plus Mosfet, and the total power is 17.4 watt. Okay, and then as usual, we want to find the thermal resistance from sink to ambient. You have to minus T sink minus T ambient, 110 minus 35 divided by 17.4, you will get 4.31 degrees C per watt. So if you want to draw it, this is the total power, okay, at this particular point. Okay, and then you will connect it to the ambient temperature 35 degrees C, and this is the curve or the slope of the RTH sink to ambient. Okay guys, that's all the example. I shown you 4 example for thermal management, and I believe if you really understand all the 4 example, you can do any question that should come out in your open book exam regarding the thermal management. So thank you. Assalamualaikum warahmatullahi wabarakatuh.